on the screen you have a drawing of a electronic device called an operational amplifier. So we are going to look in detail as to what it does, what it is, and then we are going to see how we can use these operational amplifiers to build different kinds of controls. But the very first thing is we got to understand how this little electronic device actually works. So that's the objective of our video now. So we are going to see, so we have this symbol in here. And the question is, what does this operational amplifier actually do? We have this symbol that has this this symbol is basically like a transformer. So in here we have put the difference in voltages here from an external power source to convert this voltage through this constant, this gain, into this output voltage. Let me see, let me just put in here, I am assuming in here that the voltage that we put across this this V is the ground, is a reference 0 voltage. So or to make it more clear, you could say that let's see, we'll take this one out and say that the voltage V sub 2 is, and here is the basic voltage here for this voltage difference that we are putting into this element as an external power. So basically what we want to do is to be able to convert this voltage here into this one. So how can we write this equations of the system? So first of all, let's describe what the input is. So we have the let's call it the characteristics of this element. So let's write first what is the input to this. The input is B sub 2 minus B sub 1. Okay, and we also have a what we're going to call a high impedance is a high impedance element where the current that circulates, in this case Z of I, this is big number. So these are the characteristics of this. So let's just put this as one characteristic, is 2, let's put 3, high impedance, and this is on the input side. And then you may say we have a low output impedance. Okay, so this is to say that Z on the output is 0. So in this case the constant gain is high. I'm going to say high constant gain. Okay, so you can write that you can say based on this principles, the output voltage of this device is going to be equal to A times the B sub 2 minus B sub 1 of t. Yeah? So basically what happens is this is the output here, and this is the input. So the way we read this equation is this input multiplied by this gain produces this output. But you see, this is not a passive transformer. This is what is different about this device. This operational amplifier receives external power. That is see this difference in voltage here? This is from outside. So I'm telling you what the device is in here, but the device in reality is not by itself. It's powered from the outside. So we assume that all operational amplifiers are externally powered. So basically it's a transformer with a gain. In this case is A, but in this case you see we are going to put this device into a circuit and then see what it does. So let's look at an example in here, and as you have now on the screen, we have put this device on a circuit in here. So let me first lay the foundation here as to how we are going to solve this operational amplifier. This we have the input current here, that is we have the current over here, and then we have the resistor. Remember, this is the impedance here, the resistance, and then you're going to connect it in this way. This is the operational amplifier, and it has a resistor at the top, which is actually really impedance here is just the value of the resistance. One thing that we are going to do for this device, the way this works, is that the current from here to here is 0. Okay? And so if this is 0, then we're gonna have to see what the circuit does at this node, and also what this input and this impedance do. So why don't we just go ahead and write the equations that we have, and in this particular case, remember what the basic equation was. It says that B0, B output is the gain times B sub 2 of t minus B sub 1. This is what we just did. But you see here, B sub 2, this is 0 because we have grounded here. So the equation of this is going to read that B output is minus A times B sub 1 of t. Okay? We also know that the current IA in this case, IA of S is 0. Therefore, if we examine the currents here at this, this is, here comes I sub 2, right? I sub 2. In that node, if this is I2 of S that comes down, and this is I1 of S, yeah, and this over here I just told you is IA equals to 0. Let's say that you have this way, basically if you have it that way, you will say that I2 of S plus I1 of S should be equal to I sub A, which is in this case is 0. Therefore, you can conclude that the I1 of S is equal to minus I sub 2, right? Because that's what comes out of this summation. So if this is true, I sub 2 and is equal to or minus I sub 1, or you could do it the other way also. So I sub A is the sum of these two, or you could write also that I sub 2 of S is minus I1 of S. Same equation. Okay? So remember also that I sub A is 0. Okay? So can we establish a relationship between these two that would lead us to work with this circuit plus this one? Because we have the we obviously have the output over here, the input over here, and we have the output over here. We would like to know what the relationship is between this and this. That's what we do with transfer functions, right? So in this case, we'll say that I1 of S would be equal to B sub 1 of S divided by Z1 of S, right? This I1 is B over Z sub 1. Okay, over the impedance. This is like, so that we are still use this concept like V is equal to R times I, and from here that this is this is the impedance, so you could say the V is I times R. So if this is the case, isn't it true that you can say that based on this equation right here, if we say that I1 of S is equal to minus I sub 2 of S, like this, would be equal to B0 of S. This would be B0 of S minus B0 of S divided by Z2, right? Z2 is this one right here. Yeah, this one is yeah, this is Z2. So this I2 is B out divided by Z2, right? And that's what I just wrote in here. So if this is the case, you will have that B sub 1 of S over Z1 of S is equal to minus B out of S over Z2 of S. If this is true, we have obtained a relationship between B out of S is equal to Z2 of S minus Z1 of S times B sub 1 of S. So what did it actually do? After we follow these equations in here, what did this device do? Let's interpret this. What it did is it says that the output voltage is the input voltage with a negative sign and multiply by the ratio of the impedances, which by now you know the impedance here's R on this side, the impedance is over here is R, and the impedance here is also R. So if this is R1 and this is R2, you could say for this circuit, for this particular circuit, you can say that B output of S is equal to minus R sub 2 over R sub 1 times B1 of S. This, you know, you see what it did? By the ratio of these two, this produced an inverting of the signal. So it's inverting B sub 1. So this is called inverting B sub 1. You know, it's inverting, let's see. So this is an inverting operational amplifier. So this, what have we accomplished with this little circuit in here? What we did is that by putting the circuit like this, we created a circuit that inverts a signal. That's all it does. It changes the signal, it inverts the signal based on how does it do it, or what's the value of this. It depends on the ratio of those two impedances. So we have accomplished an objective with this. So we can combine these circuits in different ways to produce different things, and that is what we will do next in obtaining different operational amplifiers that do other things.